Imagine an invisible highway stretched across hundreds of kilometers, carrying not cars, but energy itself. This highway does not just carry electricity silently. It reacts, it stores, and it responds depending on how long it is, how fast the electrical wave is oscillating, and how strongly it is pushed. As you can see on the screen, a transmission line is not a simple wire. It possesses three fundamental electrical properties distributed uniformly along its entire length. These are resistance, inductance, and capacitance. Resistance and inductance come from the physical nature of the conductors themselves, while capacitance exists between the conductors in a single-phase line, or between each conductor and neutral in a three-phase line, forming a continuous shunt path throughout the length of the line. Now here is where things get interesting. Resistance and inductance oppose current flow directly, but capacitance quietly stores electrical energy in the form of an electric field. Because this capacitance is spread all along the line, it complicates transmission line calculations. Depending on how we mathematically handle this capacitance, transmission lines are classified into different categories. And here, I want you to think of sound waves. If you shout in a small room, echoes are negligible. But shout in a long tunnel, and suddenly wave behavior matters. Electrical energy behaves very similarly. The longer the line and the higher the frequency, the more wave-like the system becomes. So the big question for you is, at what point does a transmission line stop behaving like a simple conductor and start behaving like a distributed energy system? Hold that thought. Let us start with short transmission lines. When the length of an overhead transmission line is up to about 50 kilometers and the operating voltage is comparatively low, typically below 20 kilovolts, the line is classified as a short transmission line. In this case, the capacitance of the line is so small that its effect can be safely ignored. It is like whispering in a small room. The sound does not bounce enough to matter. Electrically speaking, the charging current due to capacitance is negligible, especially at power frequency, which is 50 Hz in most power systems. From a frequency point of view, the wavelength of a 50 Hz signal is about 6,000 kilometers. Compared to that, a 50-kilometer line is electrically very short. Therefore, wave effects do not appear. The voltage and current along the line remain nearly uniform. So while studying the performance of a short transmission line, only resistance and inductance are taken into account. Capacitance is ignored, and the entire line behaves like a simple series impedance. Now pause for a moment and ask yourself, if capacitance is ignored here, why do we even bother mentioning it at all? The answer will unfold as the line grows longer. As the line length increases beyond 50 kilometers and goes up to around 150 kilometers and the voltage rises above 20 kilovolts but stays below 100 kilovolts, we enter the territory of medium transmission lines. Here, the capacitance can no longer be ignored. The line has become long enough for the electric field to store noticeable energy. It is like standing in a long hallway where your voice starts to hum rather than disappear instantly. From a frequency perspective, the line is still short compared to the wavelength, but not short enough to neglect capacitive effects. The charging current becomes significant and starts influencing voltage regulation and efficiency. However, instead of treating capacitance as continuously distributed, we simplify the problem. The total capacitance of the line is divided and lumped into discrete capacitors, usually placed at one or more points along the line, as you can see on the screen. This approximation gives reasonably accurate results without making calculations overly complex. So here, resistance and inductance remain in series, while capacitance is represented as shunt elements. The line has started to hum, but it is still manageable with simplified models. Let me ask you something. Do you think this lumped approach would still work if the line were hundreds of kilometers long? Drop your thoughts in the comments. Now we step into the realm of long transmission lines. When the length exceeds 150 kilometers and the operating voltage is very high, typically above 100 kilovolts, the line must be treated as a long transmission line. At this stage, simplifications break down. Resistance, inductance, and capacitance are all considered uniformly distributed over the entire length of the line. The line no longer behaves like a simple circuit, it behaves like a waveguide. From a sound analogy point of view, this is like shouting across a canyon. Echoes, reflections, phase shifts, everything matters. Similarly, at power frequency, even though 50 Hz is low, the sheer length of the line makes voltage and current vary significantly along its length. Mathematically rigorous methods are now employed because the exact solution must recognize that line constants are distributed, not lumped. Voltage and current at one end are not the same as at another, and they depend on distance, frequency, and line parameters. Here is an important conceptual takeaway. Accuracy improves when we respect the physical reality of the line. Short and medium lines tolerate approximations. Long lines demand honesty in modeling. Now, let us talk about performance, starting with voltage regulation. When a transmission line carries current, there is a voltage drop due to resistance and inductance. As a result, the receiving end voltage is generally less than the sending end voltage. Voltage regulation is defined as the difference between the sending end voltage and the receiving end voltage, divided by the receiving end voltage, multiplied by 100. At no load, there is no current flowing, so there is no voltage drop, and the receiving end voltage equals the sending end voltage. But at full load, current flows, impedance comes into play, and voltage drops. The difference in receiving end voltage between no load and full load conditions is what we call voltage regulation. Ideally, voltage regulation should be low, meaning that changes in load current should not significantly affect the voltage supplied to consumers. Here is a thought-provoking question for you. Should voltage regulation always be positive, or can it ever become negative? If you know the answer, write it in the comments. Finally, let us discuss transmission efficiency. The power received at the receiving end of a transmission line is always less than the power sent from the sending end. The difference is lost, mainly due to resistance of the line. Transmission efficiency is defined as the ratio of receiving end power to sending end power, multiplied by 100. Receiving end power itself is equal to receiving end voltage multiplied by receiving end current multiplied by the cosine of the receiving end power factor angle. Similarly, sending end power is sending end voltage multiplied by sending end current multiplied by the cosine of the sending end power factor angle. So efficiency depends not only on voltage and current, but also on power factor. This is why improving power factor improves system efficiency without changing line hardware. Before we wrap up, think about this. If voltage regulation is poor, what do you expect to happen to efficiency? And how does frequency indirectly influence both through reactance? Share your reasoning below. If this explanation added clarity to how transmission lines actually behave, please like the video, share it with your fellow engineers, and subscribe to the channel Electrology. Your support directly helps this channel continue producing detailed, concept-driven power system content. Also consider using the thanks button or joining the channel using the join button. These contributions are extremely important to keep this educational effort running consistently. I will see you in the next deep dive.